Okay guys, welcome back. So in the last video I talked about a situation in which the ideal gas laws can be applied, and we found the value of N, or the number of moles of the system, given the pressure, the volume and the temperature, and given the molar mass of the system, we found the mass of gas used for this task. So that was about a simple application or simple example about ideal gas laws. So in this video I will be talking about the what actually happens for the mole, right, the molecules inside the system when the temperature, and what actually happens for the molecule inside the system, and when the kinetic energy changes, and how the kinetic energy changes with temperature, and how we can derive a relationship for the temperature, and how we can derive a relationship for the kinetic energy. So all these things will be discussed under the topic of the kinetic molecular theory of gases, or KTG, right? So kinetic theory of gases I described in another video, right? I will describe in another video. So what actually happens is that from the kinetic theory of gases, I taught you that PV equals 1/3 N times M times C squared bar, right? So this is the equation that we derived from the KTG, or the kinetic theory, or the kinetic molecular theory of gases. Alright, so you know that if P, the PV equals 1/3 Nm C squared bar, so P is the pressure, V is the volume, N is the number of moles, right, and M is the total mass of the gas, and C squared bar is the mean speed, or the mean square speed of this gas. So PV equals 1/3 Nm C squared bar. So what I will do here is I will derive another equation. In order to solve the problem that we will be facing under gas laws. So what I am going to do here is that now you know that rho equals M by V. Rho equals M by V, or the density of a gas, or any solid, right? Any solid or any gas or any liquid is equal to the mass of the system, or mass of the solid, or the mass of the liquid, or the mass of the gas. So I will be using the gas here, so I will explain it in the terms of gas. So the density of a gas is equal to the mass of the gas divided by the volume of the gas. So if the gas is inside some container, the volume of the gas will be the internal volume, or the inner volume of the container. So the density of the gas is the ratio of the mass of the gas to the volume of the gas, or inner volume of the container in which the gas is being kept. So that's about density. So I'll express this equation in terms of density. So in some problems you will face in some calculations you will face problems in which there is a relationship. We have to get a relationship between the pressure, the density, and the speed of a gas, right? Or the mean speed, the mean square speed of a gas. So in those problems you need some equation. You can be deriving equations when you are given some problems under some MCQ, multiple choice questions, or longer questions, right? So you can be deriving those things. So first of all you need some equation, so that will be, you can just substitute the values and find the final value as you need. Alright, so that is the intention of this video. So if rho equals M by V, I need, if I were to substitute the value of rho, I need some mass here, and I need the volume of a gas. So I have the total mass here. I have the total mass as N times M. So this is the mass of a gas. So N times M is the total mass of this gas, and V is the volume of this gas. So what I will do is that I will isolate N times M divided by V, so that it will be equal to rho, and then I will simplify that equation so that I can derive another equation from this given equation. Alright. So what I will do is that now, in order to isolate N times M by V, I have to cross multiply 3 here and divide by C squared here. So it will be 3 times P divided by C squared bar, right, will be N times M divided by V. So as I mentioned, a little while ago, my intention is to substitute the value of rho. So since n times m divided by v is rho, I can substitute that whole value here. I can substitute the whole value rho in place of this whole quantity, in place of this whole quotient or this ratio. So n times m by v is rho. So 3 times p divided by c squared bar should be rho. So you can cross multiply c squared bar here and you can divide by 3. So p will be equal to 1 upon 3 rho times c squared bar. So that's another equation that you can derive from PV equals 1 upon 3 n times m times c squared bar. So this is from the KTG, right? The kinetic theory of gases. So from the kinetic theory of gases, you can derive another relationship like this. So why is this important? Now let's take a simple example in which we have to find the gas, right? The density of a gas. Alright. So let's assume that the density, the pressures of some gas, has been given as 1 into 10 to the power 4 into 10 to the power 5 pascals. 4 into 10 to the power 5 pascals, the pressure of a gas, and its density has been given as I'll take the value of c squared bar, right? C squared bar has been given as 100, right? 100 meters squared second to the power minus 2. I need to find the density of this system. What is the density of this gas? So this is the problem I am facing with, right? So this I've just taken a simple example in order to explain it to you. Why is this equation important? Why P equals 1 upon 3 rho c squared bar over P equals rho c squared bar divided by 3. So why such an equation is important in this content? So you can directly substitute P equals 1 upon 3 times rho times c squared bar. So you have to find the value of rho. You can isolate rho. Rho equals 3b by c squared bar. So this is 3 times P is 4 into 10 to the power 5 pascals divided by c squared bar is 100, right? No, I'll take c squared to be 1000. I'll take c squared to be 1000, right? So this is in meter, this one. So when you solve this, right, you will solve this. So Pascal is the unit of pressure. So the unit of pressure is also equal to newtons per square meter, which is kilogram meter squared per square second, divided by meter squared. Square second is the unit of what you will get is kilograms per cubic meter, right? Kilograms per cubic meter. So what actually happens is that rho is in kg m minus 3. Unit is kg m minus 3, right? So 3 here 1000, here 10 to the power 5 will be cancelled to 10 to the power 2. So this will be 12 times 10 to the power 2 is 1200. 1200 kilograms per meter cube. So it's slightly greater than the volume of the density of gas, water, right? But for most gases, the value of rho, right? The value of rho is a smaller value, right? I just took a simple example without solving this. Just took some arbitrary values, right? For most gases, rho will be of very small temperature. So let's take another example, right? Let's take another example if you are confused that, so that you will get thorough knowledge with that. Take another example in which you are given a sample of hydrogen. Sample of hydrogen H2, right? H2, and this is in standard temperature pressure, STP conditions, right? STP conditions. So what actually happen is that if this is given a standard temperature and pressure and the density as 0.09, density as 0.09 kilograms per meter cube, and the question is asking what is the value of c squared bar, right? What is the value of c squared bar or square mean, right? Square mean velocity, right? Square mean velocity of this gas, c squared bar. So if this is in STB, you know that the pressure of the gas is, right? The pressure of the gas is you'll take what to be 1 into 10 to the power 5, right? I'll take this 1 into 10 to the power 5. You can take it even in mercury, right? 760 mmHg, but it's easy to solve this, right? So I'll take this 1 into 10 to the power 5 pascals. So the temperature is actually not relevant because we know that the equation is in the form P equals 1 upon 3 rho C bar, like this. So the temperature is not relevant, so we need only the value of the pressure. So we know that P is equal to 1 upon 10 to the power 5 pascals is equal to 1 upon 3, rho has been given as 0.09 kilogram meter cube times c squared bar. So c squared bar is equal to, so this will be 0.03, right? 0.03. So it will be 1 into 10 to the power 5 divided by 0.03. So that will be 1 into 10 to the power 5 divided by 3 into 10 to the power minus 2, which is 10 to the power 7, 1 upon 3, so that will be 3 times 10 to the power 8, right? 3.3 times 10 to the power 8, right? So it's a very high velocity, right? Very high velocity. So it is 3 into 10 to the power 8, so this will be approximately 3.3 times 10 to the power 5 kilometers per second. So that is the value you will be getting for c squared bar. Alright, so that is another example in which you can put the equation P equals 1 upon 3 rho c squared. So that's just another derivation from the KTG, the kinetic theory of gases, we found in the first part of this video. And in the next part I will be explaining to you how the value of PV equals 1 upon 3 nm c squared bar, the normal KTG equation, can be used to find the kinetic energy of gases and how that kinetic energy changes with temperature. See you then.